Myself Prayak Patel, working as assistant professor in IT ICT department of LG Institute of Engineering and Technology. Now consider the today's topic. I will discuss the branch and bound technique in today's video lecture. Now consider the topics to be covered in today's video lecture. First one is introduction of branch and bound. Now next one is traveling salesman problem using branch and bound technique. And third, consider as a minimax principle. Now consider the one by one topic. First consider the introduction of branch and bound technique. Now what is the branch and bound technique? In previous video lecture we discussed about the backtracking. In backtracking we consider each and every possibilities, and out of this all the possibility we can consider or check the one by one possibility random basis. Now in branch and bound technique we consider the all the possibility initially. Out of the all possibilities consider the best possibility. Means we can say that we find the best solution or locally based solution, and out of this all consider the optimal solution, and from the optimal solution we can consider or find the next step. So branch and bound is a systematic method for solving the optimization problem. Consider here it is a generate one state space tree for the branch and bound technique according to backtracking method. So here consider the branch and bound approach is based on the principle of the total set of feasible solution can be partitioned into the smaller subset of solutions, and then consider the smaller subset and solve the smaller subset. Means this smaller subset can then be evaluated systematically until the best solution is found. So bounding functions are used to avoid the generation of subtrees that do not contain the answer state or answer node. So here we can say that the removal of the extra edges from the given state space tree. Now consider the first problem of the branch and bound technique is traveling salesman problem. Here consider the one graph. In this graph consider the A, B, C, D. Four node are there. Means here consider the four node as 4 cities, and you want to visit each and every city from the your starting city. So given a set of cities and distance between every pair of vertices, the problem is to find the shortest possible route that visits every city once and return to the starting city. Means for example, in this example consider node number 1 as a starting city. So from the city A we can start the movement or start the visiting of each and every city. So here consider initially city A as a starting point. Now consider the next city as a city B, then consider the next city as a city C, then consider next city as a city D, and after the city D move to the initial state, means starting point consider as a node A. So here consider this is a one type of traveling salesman problem. Now here consider the another example of traveling salesman problem. Here consider node number 1, 2, 3, 4 and 5. Let us look at the situation. There are 5 cities which are represented as a node. So here consider this 5 as a node. The person starting from the node number 1. So here your starting point is node 1. This person has to reach each node, and only one time you visit each and every node. So here consider the person has to reach each nodes one and only once, and they consider the back state or final state your original state or starting state. So start your visiting from the node 1 and move all the node or all the cities and back to the your initial node, means node number 1. This process has to occur with the minimum cost or minimum distance traveled. So here consider this is a traveling salesman problem. Here consider the one figure. In this figure consider the 3 node as a 3 cities. Let us say there are nodes connected as shown below. So here we can say your Hamilton cycle or Hamilton circle consider as a from node 1 to 2, then 2 to 3, then 3 to 1. Also we can say that from 1 to 3, then 3 to 2, then 2 to 1. So 1 is your starting state and 1 is your ending state, and 2 and 3 both the state are visited. So here this is considered as a Hamiltonian cycle or Hamiltonian problem using graph. So for that consider, for understanding of Hamiltonian cycle, Consider the in this figure. Here consider the node 1, 2, 3 and 4. And if we move from the node 1 to 3, then 3 to 4, then for back to the node number 1, we consider the path as a 1 to 3, then 3 to 4, then 4 to back to the node 3, then 3 to 2 and 2 to 1. So in this path, consider the node number 3 as a repeated node. So consider the CT3 repeated or visit 2 times. So this is not considered as a solution of the traveling salesman problem, or also we can say that this is not considered as a Hamiltonian cycle or Hamiltonian circuit. So for the traveling salesman problem solution, first you check your path is Hamiltonian path or Hamiltonian cycle. So consider this for understanding of that. Now in Hamiltonian cycle or Hamiltonian graph, consider the more than one Hamilton path is available or Hamiltonian circuit is available. For example, in this figure there are 4 nodes, node 1, 2, 3 and 4. And total here consider 6 edges are there. For that, here we consider one path as a from the node number 1 to 4, then 4 to 2, then 2 to 3 and 3 to 1. Now another path is 1 to 2, then 2 to 3, then 3 to 4 and 4 to 1. So more than one path are available for the Hamiltonian cycle from the given graph. Now consider the one example, and using this example understand how traveling salesman problem will work, or how we can find the solution for the traveling salesman problem using branch and bound algorithm. Now consider the example. Solve the traveling salesman problem using branch and bound algorithm in following graph. Here in this graph we have a 4 node A, B, C and D. So here consider the node A, B, C, D as a 4 cities, and here consider the starting node as a node number A, means your starting city as a node A. Now you visit the city one by one, means you visit city B or C or D first like this, and you cover each and every city. After visiting of each and every city, you move back to your original state or original node, means node number A. So here consider this figure for your example, and consider many edges are available in this directed graph. So consider the edges weight are given in this graph. Now consider the step number 1. In step number 1, first write the initial cost matrix. So here in this graph, matrix representation are there. So here consider this graph as your initial graph, and from the given graph you represent your graph into the matrix, and this matrix consider as a initial matrix. Here for representation of matrix we consider that total node equal to 4. So consider the 4 cross 4 matrix for matrix representation. Here consider the row as a B, C and D. Also consider column as a B, C, D. Now in this graph, if the path from A to B is available, then we write the distance of this path. If the distance from A to C is not available, then consider the distance as a infinitive. So if path is possible, then write the distance of particular path, and if the path is not possible, then consider the value as a infinitive for that particular path. Here consider only direct distance. Now consider the matrix as a, in first row distance from A to A equal to infinitive because no any path is available. A to B 4, A to C 12, A to D equal to 7. Then for second row B to all node distance consider as a B to A equal to 5. Then B to D equal to 18, remaining 2 as infinity. For third row C, consider the distance from C to A 11 and C to D equal to 6. Remaining 2 B and C as a infinity. Now from D to distance, D to A equal to 10, D to B 2 and D to C equal to 3. Okay, and D to D consider as an infinitive because no self edge are there. Now after the initial matrix, you consider the row reduction and column reduction operation, means consider as a reduced matrix or find the reduced matrix. Now consider how we can find the reduced matrix. For reduced matrix we consider to reduce a matrix, perform the row reduction and column reduction of the matrix separately. Means here consider sequentially, you first reduce your matrix by row, then you reduce this matrix by column. Now a row or a column is said to be reduced if it contains at least one entry 0 in it. Means any row or any column contain the one value as a 0, then this row or this matrix consider as a reduced matrix. So here consider if the row already contain an entry 0, then there is no need to reduce this particular row or particular matrix. So here consider this is your first step. Now after the understanding of how we can reduce the matrix, now we reduce this matrix by one step. Now first step is row reduction step. Now this consider as your initial matrix. In initial matrix, first you perform the row reduction operation. Now how we can perform the row reduction operation? If the row already contain at least one 0 or 10 entry, then there is no need to reduce this row. But if the row does not contain an entry 0, then reduce that particular row. Now how we can reduce this row? Select the least value element from that row. Means here for example in first row, row A. Consider the least value from the row A. Means least value means minimum value from the row A, and minimum value in row A consider as a 4. So consider 4 value as your least value. Now subtract that element from the each element of that row. Means here from the first row we subtract the value 4 because minimum value is 4. So here 4 minus 4, then 12 minus 4, then 7 minus 4, like this. This will create an entry 0 in that row. Means here consider 4 minus 4 equal to 0. So in each and every row we consider as a one value as a 0. So consider as a row reduction. Now consider the for each and every row. In first row find the minimum value as a 4. In second row find the minimum value equal to 5. In C row find the minimum value equal to 6, and in D row find the minimum value equal to 2. So this value 4, 5, 6, 2 consider as a reduction cost. So total of this 4 element consider as a cost for row reduction. Now after performing the row reduction, you perform the column reduction operation. So after the row reduction operation, your next matrix consider as a second figure reduced matrix for row. So in first row minimum value equal to 4. So subtract the value 4 from the first row. So here consider the subtract value 4 from the first row, then consider first infinitive, then 4 minus 4 equal to 0, 12 minus 4 equal to 8, 7 minus 4 equal to 3. For second row consider the second row subtract by 5. So next value as a 0, infinitive, infinitive and 13. For the third row C consider the subtraction by 6. So here consider the 5, infinitive, infinitive and 0. And for the fourth row D subtract by 2. So here you consider last row as a 8, 0, 1, infinitive as a row reduced matrix. Now after the row reduction operation, you perform the column reduction operation on that. So for the column reduction operation, you consider your resultant matrix. Means here consider the first matrix is a given matrix. Now after the reduce of row or row reduction, your matrix is second matrix. So second matrix consider as an input, and on that input consider the column reduction operation. So here consider this matrix as your input matrix. Now perform the column reduction operation. Now how we can consider column reduction operation? Same way as row reduction. So if any row containing the 0 element, then no column, any column containing the 0 element, then no need to perform the column reduction operation. But if the column does not contain the 0 entry, then reduce this particular column. How we can reduce? For reducing of any column, you can consider minimum value or least value from the particular column and subtract this value from the your particular column, then resultant matrix consider as a column reduced matrix. So here consider the minimum value from each and every column. So in first column minimum value equal to 0, in second column minimum value equal to 0, in third column minimum value equal to 1, and in fourth column minimum value equal to 0. So here only one cost is there. For column reduction, cost equal to 0 plus 0 plus 1 plus 0 equal to 1. Now after the performing column reduction operation, your resultant matrix is this matrix number 2 in figure 2. So here consider the only column number 3 subtracted by 1, only one subtraction operation is there. So here consider the 8 minus 1 equal to 7 and 1 minus 1 equal to 0 for the column number C. Okay, after the column and row reduction, consider the final cost for the your reduction cost. So here for the row reduction, you perform the 4, 5, 6, 2 value, and for the column reduction, consider the value as a 0, 0, 1, 0. So final total reduced cost equal to row reduction cost plus column reduction cost. So here consider the row reduction cost as a 17 and column reduction cost as a 1. So total reduction cost equal to 18. So your initial cost for this matrix consider as a 18. Now consider the step number 2. In step number 2, we consider all other vertices one by one. Means here consider the A as an initial node. Then after the node A or city A, you can consider path from A to B, then path from A to C, then path from A to D. Consider one by one all the possibilities. Now here initially consider the first select the vertex B, means your path consider as a path from A to B. Okay, so here consider for path A to B. Here remember some steps for performing the operation for find the solution of the traveling salesman problem. Now first consider the path A to B. Then first step is consider the old value of M A to B. Here consider the matrix name as a M. So from the reduced matrix of step number 1, in our previous step reduced matrix are there. So in reduced matrix of the step number 1, consider the value of MAB equal to 0. So here consider value of MAB equal to 0 value. So remember this value for find the solution. Now consider the second step. Here our path is from A to B. So here consider row A and column B to infinity, means set the row A and column B to infinity. So this first figure consider as your reduced matrix, and second figure consider as your resultant matrix after performing this following operation. So first operation is consider row and column B as a infinity. So here in this second figure, see that row A all the entries consider as a infinitive or set equal to infinitive, and column B consider as an infinitive, so column B entry for all the element equal to infinitive. Now after that consider the location MBA. Here path is A to B, then reverse of your path consider as your location. So consider here location MBA equal to infinity. So BA means second row, first column equal to infinity. Now consider this second matrix as a resultant matrix after performing this infinitive operation. Now after this operation you reduce your matrix, means here consider this matrix as your resultant matrix of your previous step after performing the row number A, column number B and location BA as infinitive. So here consider this figure as a input. Now perform the row reduction and column reduction. Simply we can say that for each and every path, first you consider the any row and column as a infinitive, a particular location as infinitive, then reduce that matrix. So for reducing of matrix, consider the first step is row reduction and second step is column reduction. Now first row reduction step, consider for row reduction in first row all the entries are infinitive, so ignore this line or this row. For the row B, minimum value equal to 13. For row C, minimum value 0. For row D, minimum value equal to 0. So here consider row reduction cost equal to 13. Then after performing this reduction cost, consider the reduced matrix for row as a subtract value 13 from the your second row, means row B. So here resultant matrix consider as a value 0 at location BD, because all remaining value is a infinity. So here consider this is a row reduced matrix. Now after row reduction consider the column reduction operation. So in column reduction operation consider first column value equal to 5, second consider as a infinitive, Then remaining C and D column consider as a 0 value. So column reduction cost equal to 5. Now after column reduction operation, you consider the resultant matrix as a first column subtracted by the value 5. So here consider the first column as a infinitive, infinitive, 0 and 3. Now this matrix consider as a reduced matrix for the path A to B. Now consider the cost for the node 2, because first cost consider as a 1. Now this cost consider as a 2. So cost 2 equal to cost 1. Already we find 18 as a reduced cost as a cost 1. Now sum of the reduction cost. So here reduction cost equal to 13 plus 5, and third part is value of MAB. Here consider the value of MAB as a old value in step number 1. So we already write in our previous step value of the MAB equal to 0. So consider this value as a 0. So final value of this is considered as a 36 of your answer. Now consider the next path. Here we first consider path A to B. Now consider path from A to C. So consider the vertex C as your next vertex. So consider the first step as a, in reduced matrix of step 1, consider the value of MAC equal to 7 in our previous step. Now consider the row and column infinitive. So here path from A to C. So row A and column C consider as a infinitive. Okay, see in this second figure we represent the infinitive value in row A and column C. Now consider the location as a M of CA, because path is A to C, then reverse of path consider as your location infinitive MCA. So this matrix second figure consider as your resultant matrix after the performing this three steps. Now consider this matrix as an input and perform the row reduction and column reduction operation. So for the path A to C, first perform the row reduction. Then in first row no any value, infinitive value are there, so ignore this. Then second, third and fourth, each row contain the one element as a 0. So this matrix consider as a reduced matrix for the row. So no need to perform any operation. Now consider this same matrix as your resultant matrix after the row reduction. Now consider the column reduction. For the column reduction, consider the each and every column. Here each and every column containing the 1 0 value. So we can say that this matrix is already column reduced matrix. So column reduced or row reduced matrix consider as your last matrix. Now cost for the row reduction and column reduction, and also consider the cost from path A to C. Here consider the step number 3, means cost for the node 3, A to C as a node 3. So consider the cost 3 equal to cost 1 plus sum of the reduced cost plus M of AC. So here consider the cost of 1 equal to 18, then consider the next reduced cost equal to 0, and here consider the MAC value equal to 7. So here consider the 25 as your final cost for the path from A to C. Now consider the next step, next path is path from A to D. So here consider next node as a node number D. So here consider one by one step. First is old value of MAD equal to 3 in step number 1. Now consider the, here path is A to D. So consider row A and column D as infinitive value, and consider the location as a D to A as a infinitive. So first figure, first table consider as initial table. Then second table consider the reduced table or after the resultant table after performing these two steps. Now consider this second matrix as your input and perform the reduction operation. First reduction operation is row reduction, then perform the column reduction. Now first for row reduction, consider the first row as a infinitive, second row contain the value 0, third row one value is 5, so consider value equal to 5, and fourth row contains 0. So here for row reduction, consider the third row, row C, subtract by 5. So here resultant matrix consider as your 0 value in location CA. After that consider the column reduction operation, and for column reduction operation consider each and every column, and each and every column consider the contain the one value as a 0 value. So no need to perform any operation. So here consider the after row reduction and column reduction, reduced matrix is your third matrix. Now consider the cost for your matrix. So here cost for the matrix 4. So here cost for equal to cost 1 plus sum of reduction element and value of MAD. So here cost 1 equal to already 18 plus here reduction cost equal to 5 because only row reduction are there, and plus 3 for the old value of MAD. So consider the final value as a 26 for this step. So here consider the three paths possible. From first consider node A as a root node. Now A to B, A to C and A to D. Three path is possible. So here consider the cost for one by one. First A to B cost equal to 36. Then consider A to C cost equal to 25. Then consider A to D cost equal to 26. Now after these three elements, consider the best solution. So we choose the node with the lowest cost. Since the cost of the node 3 is lowest, so we can select the or visit the node number 3. So here node number 3 consider as a path from A to C. So your final path is A to C. Means you first visit node A, then visit the node C. After that consider the A to C as your final path. Then which node is remaining? Here consider A and C as visited. Then consider the node B and D. So our next step, step number 3, consider as a explore the vertices B and D from the node 3. So here choose the node B first, then consider the node C. So here consider the next step as a node number 5. Path consider as a to C, then C to B. Because here A to C path is fixed. Then we consider two possibilities, ACB and second one is ACT. First consider ACB possibility. In this initial matrix is here. Now perform the sum operation. First operation is consider the old value of MCB. Here consider the last two element because here our path is ACP. Then consider last two element as a CB. So consider old value of MCB. So here old value of MCB equal to infinity. Now set the row and column as an infinitive. Then which row and which column consider here? Here consider the last two element only. So consider the row number C and column number B as infinitive and consider the location from last to first. So here our path is A to C to B. So reverse of this path consider as a B to A. So set M of BA equal to infinity. Now for this reduction process or this infinitive process, we can consider our input as from the step number 3, means node 3 consider as your input. So here matrix for the node 3 means when we find the path from A to C, then reduce matrix after the performing operation for the path A to C. This reduced matrix consider as your input for this path, and this path consider as a cost equal to 25. Now after that perform this operation, means row C consider as an infinitive, column B consider as an infinitive, and location BA consider as an infinitive, and resultant matrix consider as a second matrix in this figure. Now consider this matrix as your input and consider your row reduction and column reduction operation. Now here consider the row reduction operation. First row containing 13 and fourth row containing 8 as a minimum value. So for reduction you subtract the 13 from the B row and subtract 8 from the D row. So after that consider the reduced matrix as a second matrix. Now after that consider the column reduction. For here column A and column D both they contain 0 value and remaining B and C column containing the infinitive. So here consider the reduced matrix is already same as row reduced matrix. So column reduced matrix consider as a same as it is. Now consider the cost for the particular matrix. So here cost 5 equal to cost 3. Here consider cost 3 because we fixed the step 3. A to C path is fixed. So consider the cost for A to C path. So cost 3 consider as a 25 fixed. Now sum of the reduction cost at this level. So here consider 13 plus 8 and old value of MCB. So here consider the 25 plus 13 plus 8 plus infinity. because here MCB path is not possible, so value consider as an infinitive. So final value consider as an infinitive for the path A to C to B. Now consider the next path, and next path consider as A to C to D, because two possibility after the selection of A and C, B and D. So here consider the D option, means select the path A, C and D, and node number consider as 6. Now consider the value of old value of MCD equal to 0 according to our step number 2. Now consider the rows C and column D as infinitive from the this node number 3 matrix. Now after that consider the location DA as an infinitive. So after this 3 infinitive operation, your resultant matrix is second matrix. Now consider the second matrix as an input and consider the row reduction and column reduction operation. Now first perform the row reduction operation. Here both the row containing 0 element, so consider no requirement of the row reduction. After that consider the column reduction. In column reduction also containing the 0 value for each and every column, so no performing any column reduction operation. So resultant matrix is same as it is. So consider the total cost equal to cost for node 3 plus sum of the reduction cost and plus old value of MCD. So here consider the cost as 25 plus 0 equal to 25. Now consider the next step as after performing the operation or selecting the path from B and D, means after selecting path A and C, we consider our next path as a path from C to B and C to D. So here consider these two paths, C to B and C to D. For that, which value is considered for the path B and which value is considered for the path D? Here path B consider as an infinitive value and path D consider as a 25 value, because we already find these two. So out of these two, consider the best value. So here best value consider as a 25. So we select the or choose the node 6. So consider the path from C to D. So here already we fix one path from A to C. Then now we final the second path as a C to D. So our final or fixed path is A to C and C to D. Now after that performing or visiting the node A, then node C, then node D. However, now consider the next node as your node B. So perform the operation for node B only, because only node B is remaining node. So consider the node B or node 6 as your previous step. Now consider the previous step table as your input and consider and perform the next operation. Consider path from A, C, D and B. Now for that consider the old value of DB. So here consider last two element as your value. Now consider last two element column and row consider as a infinitive. So row D and column B consider as a infinitive, and location M of BA consider as a infinitive. So this is second matrix, consider as your infinitive matrix. Now after that perform the row reduction and column reduction of this matrix. So here already given matrix is reduced, so no requirement for the row reduction or column reduction. So here all the row reduction is considered as a dash, because all value is infinite. Now for column reduction also consider the infinitive value. So reduced matrix consider as a final matrix. Now after that consider the final cost for the level 7 or node 7. So cost 7 equal to cost 6 plus sum of the reduced cost plus M of DP. So here consider the cost as a 25 plus 0 equal to 25. So after that consider the final cost as a 25. And your resultant matrix or tree consider like this. After A to C, C to D, we perform the operation visit the node from D to B. So here consider next as a D to B node and cost consider as a 25. So here your final path or optimal path from the traveling salesman problem consider as a to C, C to D, D to B and B to A, and final cost or minimum cost equal to 25. So in this lecture we consider the traveling salesman problem. After that consider the second topic of this chapter is minimax principle. Now what is the minimax principle? Here first understand the minimax principle, how we can work. Now first consider the root node as a max player, and remaining or next level consider as a min player. So opponent consider as a min player and you consider as a max player. Here consider the third level as a value 3, 12 and 8. Now root of these three elements consider as a min player means opponent. Then opponent consider the minimum value out of these three means consider value 3 as a minimum. For the second node consider the value 2 as a minimum. For the third possibility, consider the value 2 as a minimum. So out of these three, consider the minimum player or select the minimum player value as a 3, 2 and 2. Now after your turn is there, so consider max player as a u, then consider or select the maximum value out of these three value 3, 2 and 2. So maximum value consider as a 3. So basically min max principle work on this criteria. So here consider it is decision rule that minimax or minimize the maximum loss and maximize the minimum profit, means your target is make minimum loss and maximum profit like this. So here consider the one example of the given problem. So here consider the 0 and cross example. Here consider one possibility is there, only 2 space is remaining in this first figure. Now if the next player is 0, then consider 0 player put the 2 possibility or 2 way to put the 0. So this 2 way consider as a your next step. After that consider the second step. Here consider first possibility as a 0 winning possibility. So consider 0 winning possibility and consider point as a -10, because if you want to play like the X or cross is winning situation. So consider the another way. In another way, if the after performing 0 at your next location, next turn is turn for the cross player, then cross player cross this particular position, then this position consider as your winning position. So consider the cross player win and consider the point as a +10. Same way second possibility also. In first case consider the 0 player as a winning player, then point for 0 win player as a -10, and if the second player is winning means cross player is winning, then consider the cross wins equal to +10. Now consider how min-max problem or principle will work. The key to min-max algorithm is back and forth between the two players, where the player whose turn it is decide the selection or move to the maximum score, means your target is find the maximum profit. In turn, the score for each of the available moves are determined by the opposing player deciding which of the available moves has to minimize cost, means your target is get the maximum profit, your opponent target is reverse of your target. So it use a simple recursive process for find the solution. Now the recurrence process for all the ways down to the leaves of the tree, and then minimax value are backed up through the tree as the recurrence value. So here consider this problem. Initially, for example, consider this is your intermediate state, because initially you start from the initial state, but for understanding purpose we consider this is your intermediate state. Now consider this as a human player and you consider as a max player. So human and system player are there. So first player is human and second player is system. So here consider human player and human player consider as a max player. Now after that consider the initial situation of the human player. Now consider the next as a computer or system player, and system player consider as a min player. Now main player consider the cross or put the cross, and human player or max player put the 0. So here consider main player put cross at 3 position, because here in first step we have a 3 possibility or 3 space. So for the 3 space we consider 1 by 1 space. So consider first cross here, then second, then third. These 3 possibility are there. In second possibility, consider the cross player consider as a winning situation, means we can say that the computer winning situation. Now after that consider the first possibility and expand this first possibility according to your opinion, means according to your human view. So here consider human possibility as a, after performing the second step, consider two possibility are remaining. So here consider first as a put 0 and second is put 0 at last position. So here if we put the 0 at first position, then consider winning situation for the human player, means consider for the max player. And in second possibility, no any winning situation here. Now consider the next step. In next step consider also first possibility for the winning player for the human, and second is not considered as a winning situation. After that consider the next step as a, consider for the system step, and for system step consider the cross for both the space, and both the situation consider for the winning situation for the system. So here consider this is example of the minimax problem. Also we can consider this problem like this. So here three possibility or three way are available. One by one space you can put the value cross or 0 alternatively. So here first player is cross player, so put the cross at 3 location. Then after consider the next location as a, in the first location consider as a winning situation for cross. After that consider the turn for the 0 player. 0 player put the 0 in both the situation. In first situation consider winning situation for the 0. After that consider this example for the, or turn for the max player, and max player put the cross and winning situation for the cross. Same way you can perform the operation for the second problem. So here consider in today's video lecture I discuss about the how minimax principle will work and understanding of the traveling salesman problem. Thank you for watching this video.